In this set of notes, we're going to introduce the idea of a derivative. Differential calculus allows us to solve different types of problems which are important in biostatistics. And we're going to look at two motivating examples. Now, each of these examples are things that you will cover in future courses, so I'm not going to go into great detail, but I do want to give you kind of an idea or a preview of how some of the skills that you're using in this course are going to be beneficial for future courses. So the first example we're going to look at is for what is called a tangent line. So in probability, the cumulative distribution function of a random variable defines the probability that a random variable takes the value less than or equal to some specified value. And so, for example, suppose that the distribution of diastolic blood pressure in a population of hypertensive women is modeled using this plot that we have. Now, diastolic blood pressure is the pressure on the arteries when the heart rests between beats, and this is the time when the heart fills with blood and gets oxygen. So just for reference, here are some different levels or categories for diastolic blood pressure. And remember that this plot is looking at a population of women who are hypertensive. So just kind of looking at this plot here, let's kind of talk first about what's going on in terms of the probabilities, and then we'll talk about how this relates to differential calculus and some of the things that we're going to be doing. So first of all, if we look here along the x-axis, we have different diastolic blood pressures. And then along the y-axis, we have cumulative probabilities. And so just for example, if we look at a diastolic blood pressure of 100, and we look at where that meets the curve, and then we look at the corresponding probability, what we can see here is a diastolic blood pressure of 100 matches with a cumulative probability of 50%, or 0.5. And so what this tells us is in this particular population, 50% of the women have a diastolic blood pressure of 100 or less. Also, in this population, now notice that normal is considered anything less than 180. So in this population of, again, hypertensive women, we can see that very few of them actually have a normal blood pressure, and that makes sense. We're only at probably about 10% here. And then we could go up even higher. We'll erase some of these lines here so we don't get our plot too cluttered. There we go. And then if we look all the way up to 120, we can see that approximately 90% of women in this population have a diastolic blood pressure of 120 or less, and so that less is important here. All right, so now let's see how we could relate this to some of the skills that we're going to be learning in this chapter and in this course. All right, so one of the things that we might be interested in is what is called the rate of change. And so, for example, let's look at between 50 and 60 on this plot. I'm sorry, not 50 and 60, 60 and 70. Give me a second to erase these lines. So here we have a diastolic blood pressure of 60, and here we have a diastolic blood pressure of about 70. And we notice that in terms of the cumulative probability, we have, very few or a very small percentage of women having a diastolic blood pressure of 60 or less, and in fact that's very close to 0. And as we go up to 70, that cumulative probability doesn't increase very much. So in other words, the rate of change from 60 to 70 is very small. On the other hand, if we look at diastolic blood pressure between 90 and 100, we see here we have a much larger change in terms of that cumulative probability as we move from a diastolic blood pressure of 90 to 100. So here the rate of change is much larger. And so in order to describe rates of change, we can actually use calculus, and derivatives, which is going to be the primary topic of this chapter, gives us a way to quantify rates of change. And so to start out with, we could look at what are called secant lines. And so a secant line, if we were interested in that rate of change from 60 to 70, so let me change my pen color here. what I could do is I could look at the slope of the line that connects these. And I can see that this line is almost flat, so we have very little change, whereas the line that connects the point from 90 to 100 has a much higher slope, so I'm having a much larger rate of change between those 2 points. Now, the other thing that we could look at is what is called a tangent line. So a tangent line, instead of looking at the rate of change between 2 points, it lets us look at a single point and what the rate of the change of the curve is at that particular point. And so how this is done is what you do is you look at what is called a tangent line. And so a tangent line essentially, and we're going to talk about it more here in just a minute, but a tangent line, what it does is it lets us look at the limit as we take this distance to 0 and we kind of move into a single point and we look at that, the slope of the line that's created there, and that slope allows us to look at the rate of change at a single point, and that's what we call a tangent line, and the slope of that tangent line is what we call a derivative, and that's going to be really the focus of this whole chapter. And so this idea of looking at tangent lines, really looking at derivatives for cumulative distribution functions, is a really big topic in BST 675. So another place that derivatives become very useful is when we're looking at minimums and maximums. And so in your introductory biostatistics course, you probably saw an example really similar to the one before, or this one that we have below. And so what I've got here is a news article, and if you want to, you can pause the video and read this news article. But essentially what's going on here is someone went and they did a poll, and they ask respondents a question, and they find that a certain percentage responds in a certain way. So for example, here for this particular poll, we had that 54% support stricter gun laws, and then they go on to say the entire sample could be plus or minus 3 percentage points. And so out of a sample of 1,110 adults. And so from your introductory biostatistics course, recall that the idea here is we have a sample of 1,110 adults. We see out of that sample, 54% of them responded a certain way. But what we're really interested in is how did the population, or how would the population respond, if the population was asked the entire question. And one way to estimate how the population will respond would be to take this 54%, which is what we call the statistic, it's generally denoted as p hat, and we construct a confidence interval around it. And so that confidence interval helps us quantify the uncertainty in our statistic, and we do that using the margin of error. And so here they're telling us the margin of error is plus or minus 3 percentage points. And so the idea here is that, again, our statistic or our point estimate is p hat equal 0.54, and we go through and we construct this confidence interval, and this gives us a range of plausible values for how the population would actually respond to this question. Now, in your introductory biostatistics course, you're given that formula, you're given that p hat, and you say, okay, we go through and we find that, they give you the formula for the margin of error and you calculate it. But what you don't discuss is, well, why is p hat? Why is that a good estimate? Why shouldn't we use something else? And how do we construct that margin of error? And it ends up that there's something that are called maximum likelihood estimators. And so that is one way to pick which statistic we should use to help, or to use as a point estimate when we go to estimate that parameter. And in order to do that, we actually find we find maximums. And so differential calculus helps us to find maximums. And so as we're going through this chapter, and eventually we'll get to this point where we'll talk about how do you find local and global maximums, just keep in mind that eventually that idea of finding maximum minimums, you're going to use that later on in your courses, and it's going to become very helpful when we start talking about, well, we know we're going to use the statistic to help us estimate the parameter, but how do we know which statistic to pick? Which one is best? Which one should we be using? And part of determining that, we'll need to be able to find maximums. All right. So we're going to start into this idea of what is a derivative, and we're going to give a formal definition for a derivative, and we're also going to give a geometric interpretation. And so what you're going to find in this section is we are going to go through a little bit of that formal definition, a little bit of that background, the geometric interpretation, which is very important. But what you're going to see is the ways that we find derivatives in this section. In practice, there's actually easier ways. And so we're going to discuss those in later sections, and I'll talk about that as we move through this chapter. So your book uses population growth as a motivating example to define tangent lines, and we're going to do the same thing. So recall that example 2 from section 3.1 of your book. In that example, we looked at a population who at size t was given by nt, and we can define the average growth rate over time on this interval where t is restricted between 0 and h. And so before we actually define that average growth rate, let's just consider a timeline to see what this would look like. So here I've got a timeline. So I'm going to put time below the line, and I'm going to put population size above it. And so what we're saying is at time 0, we're going to have the population at time 0. And at time t, we're going to have the population size at time t. And then at time h, we're going to have the population size at time h. Okay? And so when we talk about average growth rate, what we're doing is we're saying we want to look at the ratio of the change in population size over the length of time in the interval. And so if we look at, kind of this timeline, essentially what we're saying is we want to see how much did the population size change, in other words, the top part of the interval, divided by how much time has actually passed. And so a common notation that is used when we talk about a change is we use delta. And so this triangle that you see here and here, those are delta. And so delta, usually when you see it written, it looks like a triangle, but this side of the triangle is a little bit thicker. Sometimes the bottom will be a little bit thicker as well. And so delta is very commonly used to represent change. And so here, when we see delta n, that means change in population size over delta t, where delta t is the change in time. And so here, if we're looking at the interval from 0 to h, what we're saying is the time is changing from 0 to h. And so here, the length of this interval is delta t, because t is changing from 0 to h. That's how much we're changing. And then the top piece where we have the population size at time h and the population size at time 0, the difference between those gives you your delta n. And so that's what you're seeing right here. So essentially this piece is the top of that timeline that I drew up top, and this piece is the bottom part of the timeline that I drew up top. And so don't get too alarmed again by the symbol delta. Delta just means change. And so if we want to look at that ratio of the change in population size divided by how much time has passed, that here we're going to have the difference between the ending population size and the starting population size over h. And the reason we just have h in the bottom is because we started at time 0. And so this is actually called instantaneous rate of growth. And the reason for this is we're starting at time 0 and we're going up to h. And then provided that that limit exists, that's when we call this instantaneous rate growth, because if the limit didn't exist, then we wouldn't be able to find it. Now, notice that this one does require that we start at time 0 and t moves between 0 and h, but we could actually find the growth rate from any time t after h amount of time has passed. So to kind of show it this timeline is going to look slightly different but use similar notation, so I don't want you to get too confused between the two different ones. So if we draw this timeline, what we're saying is we could start at any time t, look at the population size at that time t, move h, so if I start at a particular time point and then I increase that time by h, I'm going to increase up to t plus h, and then I'm going to have the population size at time t plus h. So one way to think about this is if I start at day 20 and I want to increase or look at the change over 4 days, h would be equal to 4. So I would start at day 20, go up to day 24. And so again, here on the top of the timeline, I've got population size, and here at the bottom, I have time. So in this case, we can define what is called rate of growth, and the same thing, we're going to look at delta n over delta t. So in other words, how much does the population size change? And so notice that would be the population size change that occurs in this interval here, which would be nt plus h minus nt, and you see that in the numerator here. And then the bottom, we're looking at how much time has passed or how has time changed. So we have t plus h minus t, which just gives us h in that denominator. And so here we could look at what this could potentially look like in a picture. And so notice here on the left, what we have is a timeline where we're moving from t to t plus h. And just like I talked about in that very first example, remember that we're thinking about a rate of change. And so one thing that I could do thinking about a rate of change is I could look on that growth curve at the 2 points where I have t and t plus h, in other words, how much I'm changing. And I could look at that secant line, that line that goes between those 2 points. Now remember that in order to define a line, what I need is I need the slope of that line. And so that slope of that line I can actually define by looking at the change in population size over the change in time, because slope is rise over run. And so if I'm making a change in time t, that's going to be my run, and then my rise is going to be how much the population increases. So here the slope of that secant line is going to be the change in the population over the change in time. Now remember, I might not just be interested in, what is my rate of change between these 2 points, that secant line. Really what I might want to be knowing is how much is the population changing, or not how much, but at what rate is the population changing at a particular time point. And so if I'm interested in that rate of change at a particular time point, I don't want to look at the secant line, which goes between 2 points. What I really want to do is look at what is called the tangent line. So that tangent line is at a single point. And so one way to think of the tangent line is in this second picture. And so what the tangent line does is it says, let's decrease that space between the 2 time points and converge on that first time point that I'm interested in the rate of change at this particular time point. And what we find is that will converge to what's called a tangent line. And that slope of that tangent line is going to tell me about the rate of change at that particular point. And so since this limit, this delta n over delta t, that slope of that secant line, as I take that limit and I close in on that distance, delta t, as that distance goes to 0, what I'm going to end up there with is the slope of the tangent line. And this quantity has a special name, and the slope of that tangent line, we denote it by n prime t, and we call it the derivative. And so in other words, the derivative of x is the slope of that tangent line. And so here is that formal definition. And so notice that the derivative of the function of x, denoted by f prime of x, and so notice here we had n prime of t because our function was denoted using a capital N. So in this definition, we're using a lowercase f, is the following. And so the derivative is equal to the limit as h approaches 0. And so you might ask, well, where did the delta t go? Well, remember, delta t for this particular example with population size was the change in time, But if we're talking about functions, it might not be just t is changing. We generally denote that with an x, and so we could talk about going up by h amount. So we still have, that change along the x-axis. That's what h is really representing. It's how much did we change. And then in the numerator, we've got the function evaluated at x plus h minus the function evaluated at x. And so this is very similar to what we were just talking about with our timeline up here, except instead of talking about in terms of t and h, what we're really talking about is, if I were just kind of sketch out here some more coordinates, what we're really looking at is the change along the x-axis over the change along the y-axis. Remember, because the y-axis is where your function is evaluated. And so if we change h along the x-axis, we're curious how much did our function change, once it's evaluated. Now, this ratio has a special name. So without the limit here, this piece is called the difference quotient. Now, if that limit exists, we do say that f is differentiable at x, and the phrase provided that the limit exists is crucial. If we take an arbitrary function f, the limit may not exist. And in fact, we saw many examples in the previous chapter in which limits did not exist, and we're going to look at some more of those in section 4.2. So the geometric interpretation will help us to understand when the limit exists and under what conditions we cannot expect the limit to exist. And here is that exact picture that I was kind of, barely sketching up here. We have a much better version. And so notice along the horizontal axis we have x, and along the y-axis we have y. But remember that f of x is equal to y. We could write it as y or f of x. And so in the blue line, we have the actual curve. So the blue line here is f of x. Well, it's the coordinate points of x and f of x. But so the blue line represents the function. And so in this picture, notice what we're doing is we're going to increase from c to x. So the distance here is going to be a distance of c, so they've used c here, but that is really just h. So just be careful, we want to make sure that we're not, just looking at the letters, but really what the letters represent. And so remember that h is going to represent that horizontal distance along the x-axis. So here, h would be equal to a distance of c. Now, the 2 points that we're interested on our curve are this point and this point. If we were to draw the line between those, that would give us the secant line. And then the idea of the derivative is, again, we're going to look at what is happening to that secant line as this distance, this horizontal distance, goes to 0. And as that goes to 0, that limit of that slope is going to give us the slope of this tangent line. And so that tangent line, that's going to tell us about the rate of change at point C, and that is what a derivative is. So derivatives are all about rates of change. Now, if you've seen derivatives in the past, there are many, many ways to write derivatives. So again, we have used the notation so far f prime of x, but there are lots of different ways. And so one thing to keep in mind is that when we write a function, we could write that y is equal to x, y is equal to f of x. We have some function of x here. And so it's important to remember which one is your independent and which one is your dependent variable. And for that reason, there's different ways to write derivatives. So I'm going to write these out and then I'll talk about, the difference of them. So we could write y prime. We could write dy dx. We could write f prime of x, which is the one we just saw. We could write df dx. And we could write d dx f of x. And so all of these mean the same thing. I've seen all of them commonly used, But the important thing is, so anytime you see a prime, so notice this one and this one have the prime notation, what they are representing is the dependent portion of the expression. And so just for example, so that we have a concrete example, I could write that y is equal to x squared minus x plus 3. Notice this is the same thing as f of x is equal to x squared minus x plus 3. So for this expression, notice that everything on the left, we would call that the dependent, and x is the independent for both of these. So the prime notation looks at what could potentially be on the left and puts a prime next to it to denote that it is a derivative. The ones where you see these ratios, what they're saying is you're going to take the derivative of the dependent portion with respect to the independent variable. And so for example, if we have dy dx, notice that the y from the left-hand side of the expression is on the top and the x from the right-hand side is on the bottom. You see the exact same thing with this one right here, except it's just using the f instead of the y, but again, f is on the left side of the expression. And then finally with the last one, notice that in the top of the ratio, you just have a d. You don't have an f or a y, but instead the f of x is placed out to the side. And so your book shows how to find the derivative by application of the definition and the relationship to the tangent line. We are going to look at both here. So here we have the definition of the tangent line. If the derivative of a function f exists at x equals c, then the tangent line at x equals c is the line going through the point with the slope. And so notice that slope, that's your derivative. And then you can always find the equation of the tangent line, because if you have the point that it goes through and you have the slope, then you can write the equation of the tangent line as follows. And this goes all the way back from one of your algebra courses where you would write the equations of line. And so let's use the geometric interpretation to find derivatives. So here we want to find the derivative at the indicated point on the graph. And so here we have g of x is equal to negative 5x at the point x is equal to 1. And so I've got that plot here. And so let's first find the point on the graph when x is equal to 1. So notice when x is equal to 1, we have that y is equal to negative 5. Now notice that since g of x, which is equal to negative 5x, is a straight line, then the tangent line must also be a straight line. Now, why is that? So if we were to look at this point here, and let's say we make a small change along the x-axis, so let's say we were to go up from 1, let's just say we go up to 2 to make things easier on ourselves. And so if we go down to 2, here's another point on that line. Now, notice that the secant line that we would draw between these 2 points obviously is going to fall, if I could draw better, directly on that straight line. And so, of course, if I were to take and decrease that x-axis distance and pull those 2 points closer together, they're still going to maintain on that same line. So when you have a straight line, it ends up that the tangent line is also a straight line. And so the slope of the tangent line is going to be just the slope of the line, because they're going to fall right on each other. So in this case, the derivative of g of x is just equal to negative 5, which is the slope of the line. And so that is going to be true any time that the function you have is a straight line. So even if we had, let's say, f of x is equal to 2x. Well, in this case, the derivative is just going to be 2. Or if you had, let's say, h of x, just use a different letter, is equal to negative 100x. Again, your derivative is just going to be negative 100. And it goes back to that geometric interpretation of what a tangent line is and the fact that the derivative is the slope of the tangent line. Now, we could also look at this example. So find the derivative of the indicated point on the graph. And so here we have g of x is equal to x plus 2 squared, and we're interested at the point x is equal to negative 2. Well, notice when x is equal to negative 2, we are at 0. And so if we were to try to find the derivative here, again, if we were to think about, coming from the left and coming from the right as we decrease this distance, the only way that we're going to be able to, as we decrease this distance to reach this point and go through this point, but as we, converge from either side, what is going to end up is that tangent line is going to be a horizontal line. And so in this case, at the point x is equal to negative 2, the derivative is going to be equal to 0. Now, if we wanted to find the derivative, let's say at 1, which is here, we couldn't use this argument. It really is just a special case where we're at the very bottom of this dip that we're able to show that at that particular point g of x, or g prime of x rather, the derivative is equal to 0. We're going to need other methods to find the derivative at other points on the curve. So here we're going to actually use the formal definition, so we're going to move away from the geometric interpretation and use that formal definition to find the derivative of g of x is equal to x squared plus 1. And so to start with, what we want is we want the value of the derivative when, and that is the derivative not evaluated at x, but the derivative evaluated at 1, when g of x is equal to x squared plus 1. Now we know by the definition that g prime at 1 is equal to the limit as h approaches 0 of g of 1 plus h minus g of 1 divided by h. And so notice this is coming directly from that definition of a derivative. So I'm pulling that straight from here. The only difference is notationally I've used g to denote the function instead of f. And then we're interested at the point when x is equal to 1, so I've substituted a 1 in for the x. But other than that, it's a direct application of that definition. So notice this is equal to the limit as h approaches 0. And what I'm going to do in here is I'm going to actually evaluate g of 1 plus h and g of 1. So when I evaluate g of 1 plus h, I'm going to have 1 plus h squared, because that is the x, plus 1, minus, I'm going to evaluate g at 1, so that's going to be 1 squared plus 1. And again, I'm going to divide by h. This is going to be equal to the limit as h approaches 0. And then if we simplify this, so if you multiply out the 1 plus h squared plus 1 minus, well, obviously 1 squared plus 1 is going to be equal to 2. But you'll find that that is equal to 2h plus h squared divided by h. And then this is going to be equal to the limit as h approaches 0 of 2 plus h, which is equal to 2. And we've seen previously how to evaluate these. We do want to be careful and say, we're taking the limit as h approaches 0. We're not actually interested when h is equal to 0. We're just looking at that limit. So that's, one of the reasons it's fine that we cancel out that h there. And so what we can say now is when x is equal to 1, we have g of x is equal to 2. And we know the slope of the tangent line is 2, because that's coming from here. And so therefore, the slope of the tangent line, or probably the equation of the line, is y is equal to 2x. And I could get that, oops, going back up here, you can plug that directly into here. So notice in this particular case, we would have y minus the 2, which is equal to 2 times x minus 2, which is the value we were interested in. Or sorry, not 2, but 1 in that last piece. So in other words, I'm essentially using this equation of the tangent line to find that. And so you can double check that on your own to make sure that you do get y is equal to 2x. Now, going back up here and looking at the picture, in the red, we do have x plus 1. And then if we look at the point that we're interested in, which is when x is equal to 1, and when x is equal to 1, g of x is equal to 2, so it's this point right here. Notice that the blue line is the line y equals 2x, and we actually do see that that tangent line crosses through that point, and that the slope of that line is equal to the derivative. All right, here's another example. So we can find the equation of a tangent line to the curve at the point 2 and minus 1. So similar to before, we want the value of f prime at 2, so the derivative at 2, when f of x is equal to x squared minus 3x plus 1. So I'm going to do the exact same thing as before. We're going to use that formal definition. So we know that f prime at 2 is equal to the limit as h approaches 0 of f of 2 plus h minus f of 2 divided by h. So again, I'm just writing down directly from that definition of the derivative. And now I'm not going to do it here, but you can show it on your own, that this limit is equal to h squared plus h over h, which is equal to the limit as h approaches 0 of h plus 1, which is equal to 1. And again, I'm applying, in the background here, all of that information from chapter 1, or probably chapter 3, where we saw how to take a limit. I know, again, when I talk about the limit as it approaches 0, I'm not necessarily saying it's equal to 0. And so in this case, the slope of the tangent line, which again, that is the derivative, is 1. And then from here, we have the slope of the tangent line, we have the point that we're interested in, so we could then use this box here to find the equation of the tangent line. And if we do that, you would find the line that we have in this picture right here. And so again, we can see this tangent line touches the curve. And what this does is this is giving us the rate of change of that curve at that particular point. And so in the rest of chapter 4, again, we're going to look at several methods for finding derivatives. The ones that we're looking at here are fairly easy to apply the formal definition to or to use a graph, but in many, many cases that's not going to happen. It's going to, it'd be very difficult to look at a graph or to apply that formal definition to find the derivative. So it ends up that there are all different kinds of rules and things that can help us find derivatives that make it much easier. And so in the rest of this chapter, we're going to look at several of those rules to see, much easier ways to find derivatives.